Hello everyone, it's Richardson again here, and today in this video we will be discussing about optimizing the geometry. So in the past videos, in the Avogadro in the starting, we have seen that how to build a molecule, right? After building the molecule, you were asked to optimize the geometry. So you use the auto optimization tool, and you will be drawing your molecule in your wish, like some orientation, putting the bond, one will be large, another will be short and something. But after doing the auto optimization tool or doing the optimization, you see that the structure of your molecule or whatever you have drawn has changed, and you see energy data has been running over, and the D becomes 0, and the potential energy for that molecule has been changed. So all these process is governed by the factor called the molecular mechanics, and those activities and those structural changes are governed by the molecular mechanics and certainly the force fields. So in this video we will be discussing all the available parameters for optimizing the geometry. Okay, so let us look what is molecular mechanics. Over to your right side you can see a picture, so that I have drawn a molecule with different orientations like this. It's an example illustration. You find different types of interactions and forces taking place in the molecule when it is optimized. So just a molecule can't have its own orientation like something. It arranges itself accordingly to get into a perfect geometry. So what type of mechanics is followed by the molecule to orient itself to a perfect geometry? You find the van der Waals interaction, you have the Coulomb interaction, and these two comes under the non-bonded interaction. See, we have no bond between them. But in case you can see here, the distance, the dihedral angle and the angle all undergo distortion, and they come under the bonded interactions. Okay, so here you can see the definition of molecular mechanics, right? The molecular mechanics describes the energy of a molecule in terms of a simple function which accounts for distortion from ideal bond distance and angles. So you will draw a molecule in Avogadro, and it will be of some way. One bond will be of large, another will be some small, like that. But after giving the optimization, all these parameters come into factor when you give the auto optimization tool, and the potential energy of the molecule is calculated finally, and where it results in the dE is equal to 0, and you get the potential energy, right? So see, you have the energy, how it has been calculated. All the energy of distortion from the idealized values are summed up, and all the energy of the non-bonded interactions are summed up. As a whole, you result in calculating the potential energy due to the molecular mechanics. Here is an illustration of how you can perform the molecular mechanics using the Avogadro. You have done it already. Here we'll just have a little glimpse of it. You can go to extensions and find molecular mechanics, right? In that you can give fixed selected atoms. So how to select these atoms? It's very simple. You can go with this tool. You know, this is a selection tool. You just drag, you will get a square over, and the atoms will be selected. And when you go with these options and fix selected atoms, and those atoms will be fixed as it is, and then you go with the auto optimization tool. So when you give the auto optimization setting, which is over here, the E symbol, this is your auto optimization tool, you find that this area which you selected before is as it is, while the unselected area of the molecule can be moved. But you can stretch it over, but afterwards if you leave, it orients again and the energy gets calculated, and again if you see, it becomes D equal to 0, and the energy will be calculated whatever happens, and this remains as it is. That's all about the molecular mechanics, and you can fix the atom and do it. The next thing which you can do, the selected atom is there, no? So if you want to move that, you have the option over here, no? The fixed atoms are movable. So in the previous part it was not ticked, so you can't move that, and you can move this one. But in this case, you can see if you tick this checkbox, you can see the fixed atoms are movable. So it is movable, right? And in the next, if you tick the other thing, that ignored atoms are movable. So the ignored atoms, the all other atoms in which you have taken, and you see the entire molecules is auto optimized, and the D is finally 0, and your auto optimization is complete. See, so for the entire molecule, the auto optimization takes place, and your D is 0, and finally it will automatically come to stop. Okay, so this is all about the molecular mechanics taking place in a molecule. And now let us see about the force fields. So you found that when you click the auto optimization tool over here, you find the term called force field over here. So here you have a drop down button where you find many things are inbuilt in that is visualized over here. You find UFF, MFFF94S, MMFF94, and chemical and GAF. These are the different types of force fields available where your molecule is set into a particular electric field. Okay, so we have many force fields. Let's look one by one what we can do with these force fields. Here, the first one is the UFF, which means universal force field. What it does? Suppose you know that while drawing the molecule using Avogadro for building molecule and everything, you just choose an atom to do it. Or else if you can't find the atoms which you want, you go to the periodic table inbuilt in the software and you just select the elements, and this UFF does the job. It is capable of reproducing the most structural features across the periodic table. So this force field can optimize the geometry for all elements and does well with inorganic materials and organometallic materials. So you have to be focused that when you click on the elements in the periodic table, then you use inorganic materials and organometallic materials, you try to use the option UFF as the force field for optimizing the geometry. Then comes the MMFF94S. Here the S stands for static. Okay. So we have these two, both are quite similar, but these two are particularly used in case of organic compounds. Suppose if you are building some organic compounds like alkanes, alkenes, alcohols, phenols, and all the functional groups are listed over here, the imines, iminium cations, and you can see the guanidines and etc. You want to build the peptides also. Especially for all the organic functional groups and organic compounds, this MMFF94 force field is very much useful. So you should not use UFF for that. Instead, you use this force field. You select this one to optimize the geometry. Okay, but both has the same functional form because they both calculate the potential energy. Whatever force field you select, that job is to calculate the potential energy. Okay, so that is being done over here, but the only difference is that between these two, this one will differ in the torsion and out of plane bending, which is an additional feature included in this, and which comes with the letter S at the end, which means static due to these different parameters. Okay, it's all about the MMFF94S, and these force fields also add electrostatic charges and hydrogen bonds, which are very important and interesting feature over here, which you can see in the next slide. See, I have drawn water molecules over here, and you see the yellow color bonds, right? Now, what is that? See, I have selected the force field MMFF94S, and I can see that the hydrogen bond is ticked. Before, when you draw the molecule, this will not be ticked, the checkbox will not be ticked, but now when you click the MMFF94S, see, the hydrogen bond is added and all hydrogen bonds are shown as a yellow color dotted line. See, You can visualize the hydrogen bonds using this force fields also. So for doing with proteins or peptides or any organic molecules, if you want to visualize the hydrogen bond, this is a very good force field which we have to use in the auto optimization settings. And now let us move with the GAF. So what this expands as general amber force field. It's often used for optimizing geometries of drugs. So you know the drugs, like when you do the molecular docking, when you inbuilt a drug inside it and you want to optimize the geometry of it, you use the GAF. That's a very good force field. Exclusively for drugs you can use this force field. Okay, and it is also a common protein force field. So if you insert any protein, you can use this GAF. So you must know which force field to use for what type of compound. So for everything you can't use UFF, but UFF is a universal force field which is applicable for all molecules. But some features will not be visible when you use the UFF if you go for some large molecules, important molecules. So it is better that you use specified force field for each molecule. And you can use GAF especially for organic molecules which have all these kind of atoms: see, carbon, nitrogen, oxygen, hydrogen, sulfur, phosphorus, fluorine, chlorine, bromine and iodine, and all these kind of atoms, if your organic molecule contains, you use the GAF field. So this would serve your purpose. So in this video we have learned all a little good briefing about the molecular mechanics and the different kinds of force fields which we have to use it. Okay, so thank you, thanks for watching. You may try for many molecules if you want, and try with all these force fields in later. Now you are familiar with the Avogadro and all, right? Okay, thank you.